In proposition 11, what we're going to do is to draw a straight line at right angles to a given straight line from a given point on it. And the first step is to let AB be the given straight line and C the given point on it. So let's draw this out. So we have the straight line AB. There's AB. And C is going to be some given point upon which we're going to place that line making right angles with the line AB. The next step is let a point D be taken at random on AC. So we'll consider this to be our point D. And the next step is to let CE be made equal to CD. So we're going to place a point which is going to be approximately right there, such that CE is going to be equal to CD. And remember, we can do this by proposition 3. So what we're going to do is just place our compass right there with the center at C and the radius being CD. And we'll swing it around like so. Take note of where the intersection is. That's going to be the point E. And now the next step is on DE, let the equilateral triangle FDE be constructed and let FC be joined. So we're going to build an equilateral triangle upon the segment DE. So we'll do that using our classic construction. We're going to place the center of our compass right there at D. The radius is going to be DE. Sweep out a little bit of the arc. And then we move our compass over to E. And we let the radius be ED. Draw out some arc, like so. We take note of that intersection point right here. And Euclid calls this point F. And we finish the equilateral triangle, FDE. So F, D, over to E. And then he says, let FC be joined. So FC, here to here. That completes the construction, and now we have to show that these angles made right here, FCD and FCE, are right angles. And he says, I say that the straight line FC, has been drawn at right angles to the given straight line AB from C, the given point on it. For since DC is equal to CE, let's take note of that. He says that DC is equal to CE, Why is that true? Well, remember, we chose D at random, and we constructed CE so that it would be equal to CD. We cut off from the line CB a part equal to CD, namely CE, so those two are the same. He notes that CF is in common. And he also notes the two sides DC and CF are equal to the two sides EC and CF respectively. And the base DF is equal to the base FE. So let's take note of that. He's saying that this base is equal to the base FE. Why is that true? Remember our constructing of the equilateral triangle. So DF must be the same as FE. And he concludes, therefore, the angle DCF, so DCF, is equal to the angle ECF. He says that those two are equal. And we make that inference from proposition 8. Take note of the fact that in those two triangles, DCF and FCE, that we have side, side, side. So we can simply use proposition 8 to infer that these two angles must be the same. And he notes that they are adjacent angles. But when a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right. And why is that a right angle? That's simply true by definition. That's what it means to be a right angle. When you place a straight line on another straight line such that it makes these angles equal, by definition 10, that's what Euclid means by a right angle. Therefore, each of the angles DCF and FCE is right. Therefore, the straight line CF, that's that straight line CF, has been drawn at right angles to the given straight line AB from the given point C on it. And that's all.